Okay, hey everybody, I started recording just a bit before so I won't miss it during. I just want to make sure with all the panelists that it is okay, and to remind you that we'll put those videos on YouTube later on. So if you have problems please let me know now. Otherwise we'll continue with the recording and all is good. Okay, thank you. I'll put myself to mute and I'll probably stop my video, but if anything is necessary, I'll be here, and Yusuf, I'll also start the videos when you'll tell me.
Okay, thank you, Igor.
Thank you.
So maybe just a few minutes, and then at 2 p.m. we can start recording.
Yeah. No, I already started recording now, just so we won't forget. There's no reason not to.
Okay, I'll give you the start for the videos. Okay. Thank you.
Perfect. Thank you.
Maybe we can start. Okay. Hello, everybody. I am and welcome to this ConcurA session. I am Yusuf Olaj. I'll be chairing this session. I also assume that everybody is by now familiar with the Q&A functionality. And I recall also that if you want to ask questions, but at the end of the videos, you can raise your hand and the panelists will unmute you so you can give your question. So the first talk will be given, I guess, by Patrick. And Igor, could you please start the video of Patrick?
Hello everyone. I'm going to talk about transients in countable Markov decision processes. This is joint work with Richard Meyer, Stefan Kiefer, Masashim Mohammadi, and my name is Patrick Tosco. Transience is a new objective that essentially asks that no state is visited infinitely often, which of course only makes sense in infinite state MDPs. What we're really interested in here is how complex good strategies for this new objective need to be. And it turns out that there are really simple good strategies for transients, namely memoryless and deterministic epsilon optimal strategies, as well as optimal ones where they exist. First of all, I will not have to convince you that MDPs, Markov decision processes, are pretty much everywhere. They are a standard formal model for dynamical systems with both stochastic as well as non-deterministic behavior. They're used in AI, for example, for modeling machine learning processes, control theory, operations research and finance, and especially in formal verification. MDPs are often depicted as graphs with two types of nodes or states. Random nodes, these are drawn as circles here, and they come with a fixed distribution over the successor nodes, and thereby determine the probability of moving to one or the other successor. And the second type of node are controlled nodes, here drawn as squares, where a controller or also player can determine the distribution that determines where to move next. Now, a play, also a run, is an infinite path through this graph, and objectives are simply measurable sets of runs. Now, the player aims to maximize the probability of that set, meaning the chance that the generated run ultimately is in the given objective set. And the strategy tells this controller which distribution to pick at any given point in time. So now a strategy, of course, may depend on the prior history of the run. And typically we classify strategies in 2 dimensions, memoryless versus history dependent. Does it take the history into account or not? And we also, the other dimension would be deterministic versus randomizing. Deterministic means you pick a Dirac distribution. So you surely go to one specific successor. In this classification, the simplest possible strategies would be MD ones, memoryless, and deterministic ones. Finite MDPs are especially simple in that many objectives admit MD optimal strategies. For example, if you look at this MDP here, and let's say you aim to maximize the chance of reaching the green target state, then you can easily see that the best possible move from this choice node is always going to be the one that goes right and up. And this strategy is, of course, MD. And this is no coincidence, because for finite MDPs with reachability objectives, there always exists an MD optimal strategy. And this is even true for much more general parity objectives, and even true for much more general turn-based stochastic 2-player games, where you not only have the player and the randomizer, but also an adversary. If the state space is infinite, then things get much more interesting. For example, consider this MDP here, where from some initial state S, you can continue to go upwards, some infinite ladder, or you can decide eventually to move right and branch off from the ladder. And let's say the aim here is again to reach the green target node, which of course means you are implicitly aiming to avoid the bottom middle state, which is a deadlock from which you can never see the green target node again. We define the value of an objective, say E, as the supremum probability of a generated run being in that objective, so the supremum probability of that objective set over all possible strategies. In this example, the value is 1. As for any fixed epsilon, you can guarantee reaching the green state with probability 1 minus epsilon by going high enough. So for example, you can move up twice and then commit to going to the right. That introduces an error of 0.5 times 0.5. So 1 over 4 is your chance of getting stuck, and the rest is the chance of reaching your target state. Still, there is no optimal strategy, one that actually achieves a probability of 1, which is the value of your objectives. And this is, as you can see, if you continue to move upwards and never commit to going right, then in fact the chance of reaching the target is 0. But as soon as you commit to moving to the right, you immediately introduce a possible error, which is simply the product of all these down arrows towards the dead end thing. So any possible strategy will introduce some error and therefore not achieve the value of 1, of probability 1. So even in this infinite state MDP, for reachability objectives, there's always an epsilon optimal strategy, which is MD, and this generally holds. However, this need not be the case for all objectives. If you, for example, look at reaching the target repeatedly, meaning you look at the Büchi objective, then you cannot use the same strategy as before. And in fact, no MD strategy is any good. All MD strategies achieve a value of 0 for the Büchi objective. And this is intuitive because any MD strategy will commit to moving to the right at one fixed height. So every time you restart the process, you will introduce the same error, the same chance of in this round dropping into the red sink. And therefore, if you do this infinitely often, then almost surely you will eventually end up in the sink and essentially you die. But still, the value of the Büchi objective is 1. There is always an epsilon optimal strategy here. There's just no MD1. And the way you get an epsilon optimal strategy is not by fixing the height at which you committed, but by varying it. In each iteration, you go ever so much higher before you commit to an error and going to the right, in such a way that the cumulative error is still less than the one that you're trying to achieve. Our main question is, how complex does a good strategy need to be? Where good can either be epsilon optimal or optimal, and complex means the internal complexity of the strategy, what type of memory the strategy needs. Either no memory at all, finite memory, or infinite memory, and then what type of infinite memory. And the answer, of course, depends on several things. For one, it depends on the objective. It might depend on whether or not you want optimal or epsilon optimal strategies, the type of MDP, so is it finite, is it countably infinite, uncountably infinite perhaps even, and it also depends very much on the branching degree. Is the branching degree finite or infinite? The type of results that we're interested in is, for example, like this one. This is a theorem that appeared in ICA 2019. It says, in countable MDPs with Büchi objectives, for epsilon optimal strategies, a step counter plus 1 bit of memory is necessary as well as sufficient. In this paper, we study a new objective called transience for Markov decision processes. First of all, let's remember that for Markov chains, which are just MDPs without any choice nodes, a state is called transient if the probability of revisiting that state is strictly less than 1. A transient state is almost surely, with probability 1, only visited finitely often. For example, the state on the left here is transient, whereas the one on the right side is not. It's called recurrent. Now we can generalize this to MDPs as follows. Let's change the example so that the state on the right hand side is a choice node where you can either stay or go back to the initial left node. Now if you aim to make, let's say, the left node transient again, there's a strategy that allows it to do that, namely to just stay where you are, continue to loop, and put no probability mass on the back edge. In fact, if you aim to make a finite set of states transients, then this is pretty much the same as the Büchi objective, which is obviously a parity objective. So, and we studied this before, there's nothing to see here. Instead, we define transience as the objective that asks that every state is visited only finitely often. More formally, we can write this in kind of an LTL notation here. It's a countable conjunction over all states in S, the set of states, that asks that eventually globally not S. So eventually there is a point where you never see the state S, and this should hold for all states S. If you write it like this, it's quite natural to see that this is in fact a Borel definable objective. It's a countable conjunction over, countable disjunctions, etc. But in fact, it's not definable as a parity objective with finitely many colors. Still, this objective is tailed, meaning it only depends on an infinite suffix of a row. So why is this interesting? Well, intuitively, transience captures the intuition of making progress. Every state is eventually left forever. And this can be useful, for example, if you want to define an MD strategy in some area of the infinite state space, and then the transients, if you also satisfy transients, then this guarantees that making this decision at this point will not hinder you in an ultimate future. Let's look at a couple of examples. This here is a Markov chain representing a classical gambler's ruin process, which is an infinite ladder of nodes representing different levels of wealth. And at each point, you toss a coin. With probability P, you go up one level, and with probability 1 minus P, you go down. And you're ruined if you reach the wealth level 0. Now, it's well known that if your probability P is less or equal than 1/2, then starting with any wealth level I, the chance of ruin reaching the level 0 is in fact 1. So this means that the probability of the Büchi objective for the ruin state 0, if you make it a losing sink, is in fact 1. And this also then means that the transience objective, as we have defined it, has probability 0 because this one state at the bottom will always be recurrent. And this is, of course, you don't have any choice nodes, so there is no strategy. Now, however, if you have a probability P being strictly bigger than 1/2, then the chance of visiting any state infinitely often is in fact 0. For no matter the starting state, no matter the state that you pick, the Büchi objective for that state will always be 0. And this in fact means that every state will be transience, so the transience objective is equal to, or the probability of transience is equal to 1. And so what this goes to show is that transience is not just a property of the structure of the graph, but in fact it requires some arithmetic involving the transition probabilities. Let's have a look at a slightly more interesting example, which is also kind of a gambler's ruin situation, but you get to choose whether you want to continue gambling or cashing in on your current wealth, or in this case, value of transience. In fact, it's a long chain. There's just a repetition of this one gadget, which I highlight here in the middle. And basically what it is, you should be looking at the states xi at the bottom. These only go to the right and they can never come back. So they are transient for all possible strategies, and therefore for any possible strategy, the transience objective has a value 1. Similarly, trivial, if you look at the bottom states, which can actually be the same state, it's an unsuccessful sink. It's a self loop, and therefore it is recurrent no matter what. So the transience objective has value 0 from this sink state. Now, if you look at the state in the middle, R, that is a random state that with probability 1/2 to the I goes to the unsuccessful sink, and with the remaining chance goes to the successful infinite ladder, right? So the value of transience from those states is 1 minus 2 to the minus I. The only interesting state really is the choice node at some wealth level I, where you get to pick either to commit to the to getting the value of the corresponding R state, or you decide to go to stay on the ladder and continue to gamble. Now, the ladder on top is in fact a gambler's ruin situation with a fair coin toss. So probability 1/2 you go up, and with probability 1/2 you go down. And let's allow ourselves a restart at the bottom, so you're not dead there. So this means that in fact, as long as you stay on the top ladder, every state will be recurrent, because almost surely you will see every state infinitely often. Yeah, the value of transience will be 0. If you commit at some point, then still the value of transience will be strictly less than 1. And this is because once you commit to a particular error introduced by the chance of going to the sink node at this level of wealth. Still, the value of transience equals 1, and this can be seen by a very simple strategy. Let's call sigma j the strategy that cashes in above wealth level j. And this, of course, ensures that the value of the transience objective will be at least 1 minus 2 to the minus j. And this, in fact, is totally regardless of the starting state. So this is a strategy which will be 1/2 to the j optimal, so because that's the error that you introduce at most. And notice also that this strategy is memoryless and deterministic. You fix a choice at which point you are happy with basically cashing in the value that you could get. Before that, you continue to play. So eventually, with probability 1, you get to this level where you can cash in. Right, so what we have shown, that's one of our main results, is in fact that this is no coincidence that, that there is an epsilon optimal strategy, which is MD. So our theorem says that for every countable MDP and for every epsilon, there is a uniform epsilon optimal MD strategy for transients. And moreover, there's a single MD strategy which is optimal for every state that has an optimal strategy. On the last point, if we go back here, the strategy that I declared here is of course also optimal for the bottom, the R, and the X states, because there's nothing to choose here, right? So this one strategy will be 1 over 2 to the J optimal, no matter where you start. Notice that in this theorem, there's no assumption on the branching degree. And this also holds, in fact, for multiplicative error, which is a bit more fitly to prove. And in fact, this contrasts earlier results on parity. For example, the safety objective needs a step counter. And the Büchi objective, as I have shown you in an earlier slide, in fact needs a step counter plus an additional bit. For comparison, let me briefly show you earlier results on the strategy complexity for parity objectives. These two images here should be considered independently. So the one on the left considers epsilon optimal strategies assuming infinite branching, and the one on the right considers optimal strategies for infinite branching, optimal strategies where they exist. So the different levels represent the different levels of the Mostovsky hierarchy. So the number of different colors that you would need to define your objective using it as a parity condition. So at the very bottom here are the reachability objectives, which are super basic. They have MD epsilon optimal strategies. And even for safety, you need a step counter. And for 0-1 parity, which is co-Büchi, you also need a step counter. From 1-2 parity, so Büchi, upwards, you need not only the step counter, but you also need an additional bit. And these strategy complexities are lower as well as upper bound. So these are necessary and sufficient. So what we've shown in this paper is that transience lives very close by the reachability objectives. The next thing that we did in this paper was we considered MDPs where transience is kind of baked in. We considered a class called universally transient MDPs, which are those MDPs where every possible strategy satisfies transience almost surely. Now notice that this strictly subsumes acyclic MDPs. Every acyclic MDP is necessarily also universally transient, but this does not hold vice versa. Just think about the gambler's ruin situation with unfair coins. That is universally transient, but not acyclic. So what we did is we looked at the strategy complexity for parity objectives, assuming that the underlying MDP is universally transient. And what we showed is that if you look at 0-1 parity objective, then for any epsilon, there always exists an MD epsilon optimal strategy, which is also uniform. And for 0-1-2 parity objectives, there always exists a single MD strategy, which is optimal from all states that have an optimal strategy. This is the picture that I showed you before, but assuming universal transience. You see that the safety as well as 0-1 parity objectives now admit MD epsilon optimal strategies, even in the infinite branching case. And on the right-hand side, you see that all objectives up to 0-1-2 parity now admit MD optimal strategies for states where that exists. The lower bounds, so the fact that one additional bit is necessary from objectives 1-2 parity upwards for epsilon optimal and 1-3 parity upwards for optimal, this already holds true for acyclic MDPs, and it was shown in the earlier ICAL paper. All right, this is everything I wanted to show you in this presentation. I invite you to read the details in the paper version, and if there are any questions that you might still have, feel free to contact me by email. This is my address. Goodbye.
Thank you, Patrick. So I don't see any questions in the Q&A. also don't see any hands raised. So while people are maybe writing their questions, I can start by one. So sometimes in stochastic systems, when the problem is very difficult, instead of asking quantitative questions, we ask questions about the qualitative strategies. For instance, if it is possible to ensure something with probability 1, almost surely or just positively. I was wondering if the problem becomes easier if you ask the questions if the transients hold only almost surely, and you don't consider the value problem.
Well, depends what you mean by easier, right? So none of these results are computational. So it's not like we would take some input and then, show that something is decidable or measure the complexity or so, because
Yeah, sure, but maybe the strategy, the complexity of the strategy.
It could be. I haven't considered that. I would imagine it's simpler, but I mean, it can't get much simpler than MD, right? So you would have to consider kind of MDPs where where you would have to look at optimal strategies for MDPs where they don't from starting states where they don't exist. No, I don't want to say anything wrong. I don't really know. I haven't considered this. But I mean, just the point I'm making is that it doesn't get very much easier than MD strategies. So I wouldn't know what else, how much easier to get it. And you see that these results are not just MD, but they are universally, uniformly MD. So
I had also a question about this. So in Theorem 1, you wrote uniform epsilon strategy, and then you wrote something about optimal strategies from every state. And I always thought that uniform strategy means that you don't fix the initial state and the strategy is optimal, epsilon optimal. So I don't know, what do you mean by uniform? Maybe I've missed it.
So this is what we mean by uniform. So
okay, so it's the same.
Uniform would mean that it's for every state, for the fixed epsilon, for every state, this strategy, if you follow it from this state, achieves value 1 minus epsilon, or value minus epsilon.
Okay. I still don't see anything from the audience. So maybe one question. So you considered MDPs, and I assume that for the two-player case game, for stochastic games, it should be very difficult. But as I understand, the transience is somehow it generalizes the notion of acyclicity, which sometimes brings some ways to handle the model. And I was wondering if it makes sense to consider stochastic games where you play only against transient strategies of the opponent.
Oh. Okay, so first of all, there's no such thing as a transient strategy, right? You would have to define as something like a strategy is transient if against all player strategies in that case.
Yeah, or I
gives you a transient.
I can risk a definition on the fly. So for example, you can say that when you fix the strategy, the MDP you get is universally transient.
Yeah.
And what happens there? I don't know. Maybe it doesn't
question.
Make
we
sense.
Haven't considered. It's a good question. Yes. But so for games, these things get tricky because I'm quite sure you can encode things like strategy lower bounds for objectives like reachability or so. I mean, especially I mean, if you're greedy and go even further to concurrent games, then you have lower bounds of step counters plus bits and so on for simple objectives like reachability. And then so I agree. It will get more complicated, and it's a good direction of trying to utilize the transience idea and push this forward. we have
Okay, thank you. So maybe we can, if I still don't see any questions or hand raised, so maybe we can carry on with the second video. Igor, please.
Thank you.
Thank you, Patrick.
One moment.
Okay.
I have
Okay.
I'm sorry, one moment.
Okay, Igor, I think there is a problem with the video. It seems that we can't get the sound from the recording.
One second. Some technical difficulties.
Hello,
Do you hear
I'm
it
Eric
now?
Monday, and I'm here to talk to you about my joint work with Richard Meyer on the strategy complexity of mean payoff, total payoff, and point payoff objectives in countable MDPs. So, a countable MDP, or Markov decision process, is a transition-based game where there are player-controlled states represented by squares, random states represented by circles, and rewards on the transitions. They can additionally be finitely branching or infinitely branching. Objectives are sets of runs satisfying certain conditions. The player wants to maximize the probability of these objectives. The ones we consider in particular are the limit for the point payoff, the objective to push the limit of the pointwise rewards above zero, the limit for total payoff, which is the objective to push the limit of the total reward above zero, and the limit for the mean payoff, the objective to push the limit of the average reward above zero. That is to say, total reward so far divided by steps taken so far. So first, here is an example where all three objectives are satisfied. Point payoff is satisfied because eventually, as in from the second step, all of the rewards are positive, so that clearly satisfies a limit above zero. Total reward is satisfied because once the reward gets down to -1, it then converges towards 0. Mean payoff is satisfied because the total payoff is satisfied. Secondly, here is an example where only the mean payoff is satisfied. Point payoff is not satisfied because infinitely often the reward is -1, so it's -1 plus 1 -1, so the limit in this case is -1. Similarly, total payoff is not satisfied because the total reward oscillates between -1 and 0, so the limit of the total payoff is also -1. Finally, mean payoff is satisfied because the limit of mean payoffs is -1 over n as n goes to infinity, n being the number of steps taken so far, and -1 over n clearly converges towards 0. Therefore, the mean payoff is satisfied in this case. So, how much memory does a good strategy need? The answer depends on the objective, point payoff, total payoff, or mean payoff, whether we're considering epsilon optimal or optimal strategies, the type of the MDP, in our case countably infinite, and whether the MDP is finitely branching or infinitely branching. This is in particular the out degree of a vertex. So let's have a look at our results. The types of strategies that we consider are those that use no memory, that are memoryless, those using a step counter, and or those using a reward counter. A step counter is a clock. It simply keeps track of the number of steps taken so far, and a reward counter keeps track of the total reward that has been accumulated so far. So, for example, if we have a look at epsilon optimal finitely branching total payoff, we show that it requires only a reward counter. And all of the strategy complexities given in this table are both upper and lower bounds, so in this sense they are tight. Furthermore, all the strategies are deterministic and randomization does not help anywhere. In order to pin down the strategy complexity of an objective, we need to exhibit both a lower bound and an upper bound. A lower bound is obtained via an example of an MDP in which the objective can be satisfied whilst playing correctly, but cannot be satisfied without access to the right kind of memory. An upper bound, on the other hand, is a proof that good strategies exist which use only a certain amount or type of memory. So, without further ado, let's have a look at in more detail how we obtain the lower bound that epsilon optimal total payoff in finitely branching MDPs requires at least a reward counter. And we show this in the sense that the step counter with finite memory is not sufficient. What we see now is the nth gadget in our MDP. So our MDP is constituted of these gadgets chained together off to infinity. So, and each gadget is composed of a random state with branching degree kn plus 1, followed by a player controlled state also with branching degree kn plus 1. This kn here is a slow growing but unboundedly growing function, and it gives us the branching degree in the nth gadget. So probability delta Jn is simply the probability of taking the jth transition, and then the probability here, epsilon Jn, is a probability of, after taking the jth transition, of falling into this losing sync state here. So this just represents an infinite chain of -1 states, and it is losing. The numbers mn are very large positive integers, giving us the rewards on the transitions. So let's have a look at what a run through this gadget might look at. We start in a random state, then, for example, we take transition 1 with probability delta 1, we pick up mn reward and we arrive in state Cn. Now, what we want to do is ideally keep the total payoff above 0. So what are the ways of doing that? Well, we can either take this first transition and lose exactly the same reward as we had before, or we could take the 0th transition and save up some reward and keep our total reward above 0. So both of these would allow us to keep our reward above 0. However, what we've done is we've carefully balanced the delta probabilities against the epsilon probabilities in such a way that matching the delta to the epsilon means that we have a relatively high chance of surviving, whereas if we play conservatively and choose to try to save up reward, well, the odds are against us and we're more likely to fall into the losing sink. And this holds for all of the deltas. So going delta j to epsilon j is fine, but going delta j to epsilon 1 or epsilon 2 would not be fine. And on balance, you would end up in the losing sink. So the intuition behind winning in this gadget is that you always have to match. So we want to remember, if we've come from the jth transition, we want to know that we go to the jth transition in the player controlled state. However, matching requires memory. So to play well in each gadget, you need to at least be able to remember kn+1 things. You need to remember which transition you've come from. However, as the gadgets go on, kn grows unboundedly, so any finite bound will eventually be overtaken. So in order to play well in every single gadget, you do genuinely need to have infinite memory in order to, well, keep being able to keep track of which random transition you've come from once you arrive in the player controlled state. Then, due to the way we've balanced out the epsilons and the deltas, matching the delta to the epsilon every single time gives us a positive probability of surviving and also keeps our total reward at 0, which is completely fine for limit of total payoff. Whereas if we don't match, we're either going down and sacrificing too much probability of going into the losing sink. And if we go down infinitely many times, then we're going to fall into the sink with very high probability. Whereas if we go higher than we were in the random transition, then we're just tanking our total reward below zero. And that also cannot happen infinitely many times, because then the limit would genuinely be below zero. So this gives an indication of how we can survive with a positive probability, but it doesn't tell us how to get epsilon optimal strategies. So in order for epsilon optimal strategies to exist, we chain the gadgets from the previous slide together and allow skipping ahead in order to enable the chance of winning to be pushed as close to 1 as possible. So this is S0, then these black boxes represent gadgets, just like on the previous slide. So this would be gadget 1, this would be gadget 2, this would be gadget 3, so on and so forth. So we know that if we match in every single gadget, we have a positive probability of surviving. But that's not good enough an epsilon optimal strategy, because we want to push the probability of winning above 1 minus epsilon. So in order to do this, we engage with this ladder, which just allows us to skip gadgets. We can't skip ahead forever because of this -1, but we can skip for arbitrarily long as we eventually engage with the gadgets. So we skip ahead, pushing our probability of winning above 1 minus epsilon, and then we engage with the gadgets as late as we need to, and then match from there on out. Additionally, we've got these 4 steps in here just to keep the path length in the gadget constant. So the gadgets had 4 steps in each of them, 1, 2, 3, 4, and we match that here in our skipping ahead, just so that our MDP remains acyclic and the step counter cannot help us because the step counter is built into the MDP. Now let's have a look at an upper bound. In particular, we're going to be looking at how to obtain epsilon optimal strategies in finitely branching point payoff. So we need to consider a finitely branching MDP M, and we begin by partitioning M states into 2 sets, S safe and S without safe, S safe. S safe is those states from which it is possible to almost surely see only rewards above 0 forever. So in other words, S safe are states in which we can run a safety strategy in which it sees only positive reward transitions forever, and if you can do that almost surely, then you're definitely going to win epsilon optimal point payoff. So we fix an optimal safety strategy, sigma safe, in S safe and construct a new MDP, M prime, which is exactly like M. However, all of the states in S safe are replaced with the following gadget, which is a chain of +1s. So if we could win by reaching a state in S safe and just running an almost sure safety strategy, which wins with probability 1, then it's exactly the same as arriving in this gadget and also winning with probability 1. So clearly, the probability of winning in M prime is the same as winning in M once sigma safe has been fixed in S safe. We now notice that satisfying the point payoff objective is the same as eventually never seeing rewards below every negative bound. So in accordance with this, we define safety I to be the objective of never seeing rewards below -2 to the -I, and accordingly we write that point payoff is the intersection of eventually accomplishing safety I for all I. We can now observe a general epsilon optimal strategy for point payoff. With high probability, it will eventually stop seeing rewards below -2 to the -I for all I. Hence, for each I, there will be an n sub I, such that after n sub I steps, safety I will be satisfied. Accordingly, we split M prime into sets bubble Ni, those states reachable from S0 in fewer than Ni steps. Now we split each bubble into safe and bad sets of transitions. Safe I transitions respect safety I inside of bubble Ni, whereas bad I transitions do not. So if we have a look at bubble N2, these are all of the states which are reachable in fewer than N2 transitions. And once you're outside of bubble N1 and inside of bubble N2, we're either in safe 2 or in bad 2. Safe 2 are those transitions which have reward which is strictly higher than -2 to the -2, and bad 2 are those transitions which are worse. So as we're observing our epsilon optimal general strategy, we're noticing that with high probability it will stay within these safe sets, and with very low probability it will end up in the bad sets. So we now construct a new MDP, M double prime, which is just like M prime, but all transitions in bad I now lead to a losing sink. So this is to represent the intuition that with high probability, the general strategy stays in the safe sets, and with very low probability, it will end up in the bad sets. And we won't actually lose too much by just transforming those bad sets into states that just lose straight up. So transforming bad I sets into losing sinks won't lose us too much probability of winning. But what this has done is this has made winning point payoff inside of M double prime equivalent to being transient. So if you recall before, we turned all of the sets in safe into these long ladders of +1s. We turned all of the bad sets into just recurring loops on a losing state. So the only way to win now is by staying in safe and going out forever. And note that you have to visit every single bubble because our MDP is finitely branching, so you can only actually spend a finite amount of time in each finite set. And because of finite branching, each bubble is finite, therefore you eventually have to leave every bubble forever. So the only way to lose is by being recurrent inside these losing sinks. The ways to win are by visiting all of these safe sets, or by falling into a winning ladder in S-safe as illustrated on the previous slides. So why is staying in these safe sets winning? Well, by definition, safe 1 sees rewards only above -2 to -1, safe 2 sees rewards only above -2 to -2, so on and so on. So if you eventually stop seeing rewards below -2 to -I for every I, then you're converging to 0, which will satisfy a point payoff. So that is to say that all we need to do is be transient in order to win. Transience is a property of eventually leaving every single finite set behind. We know that epsilon optimal transients can be achieved MD. This is a result from transients in countable MDPs, another paper that's appearing in the conference this year. And from that, we know that transients can be achieved memoryless deterministically. So all we need to do is then carry this MD strategy back to M. This only has a small 3 epsilon overhead. We lost 1 epsilon looking at the general strategy. We lost another epsilon turning these bad sets into losing sinks. And then we lost a 3rd epsilon by observing this epsilon optimal transient strategy. And since this holds for every epsilon, we get our epsilon optimal strategies, giving us our result. Thank you for listening.
Thank you, Eric. I'm checking if there is any hands raised. I can't see any. Since that there is again no questions, and maybe we are running a bit short of time. So I have just a quick question. It seems that you're considering the inferior limit in your setting.
Yep.
And I was wondering, does it completely break when you consider the superior limit, or can the results easily carry on?
So results to come on the limb soup.
Okay.
That's currently what we're working on, and the results are fairly different. Limb inf is in a sense similar to Kobuhi, in the sense that you eventually always want to kind of avoid this bad thing, whereas limb soup is kind of more similar to Buhi in the sense that you always eventually want to see this good thing.
Okay.
So it's fairly different.
But do you mean the consequence on the nature of strategies is different, or only the technical core?
So even the strategy complexities are kind of a fairly different field. They still kind of involve step counters, reward counters, and bits, but the landscape is fairly different.
Okay. Okay, thank you. So maybe we can carry on with the last video of this session. Igor, please. Thank you, Eric.
Yeah, no problem.
Hello, I'm Jingyi. In this video, I'm pleased to present our work on model checking quantum continuous time Markov chains. This work is completed jointly with Mingxu, Jiguan, and Nengkun Yu. There are lots of results on model checking classical Markov chain for both discrete time and continuous time. As recently quantum computation develops fast, there is an urgent need to develop effective verification techniques to improve trustworthiness of quantum systems. So the counterpart model of quantum system has been considered in these years. For instance, the quantum discrete time Markov chain. However, continuous time system is more realistic in physical world, especially for quantum system. It's natural to ask how to verify a quantum continuous time Markov chain. And before I introduce our model, some basic knowledge about quantum computation should be reviewed. The basic state in quantum system can be described as a vector, all of which span a Hilbert space. A more useful way to describe quantum systems is density operator, which is a positive matrix with unit trees on the Hilbert space. As vector representation is only suitable for basic states known as pure states. Besides pure states, there are also some states which are the mixture of the pure states, known as mixed states. And there are two kinds of systems, named closed system and open system. Closed system means a physical system that does not interchange matter with another system, while an open system interacts with an external system, which is known as the environment. Well, imagine, for instance, a thermos with hot water, where the water is isolated from the outsider, thus it can be seen as a closed system. While in the red picture, there is a pot with boiled water, where the water turns into vapor and rises into air. The fire keeps heating the pot. It can be seen as an open system. In quantum system, the time evolution of a closed system is described by the Schrödinger equation, and Hermitian operator in the equation defines the transition of the system. And the time evolution of an open system is described by the Lindblad's master equation. The equation may look complicated, so let's look into it more carefully. Well, the whole equation can be divided into two parts: the internal system, the blue part, and interaction with the environment, the red part. The blue part actually is consistent with Schrödinger equation. To characterize the evolution of an open system, it's necessary to use those linear operators LG beside the Hermitian operator H. The solution of the equation is a system state that changes over time. To get this solution, we use the following fact about matrix transformation, where L2V function is short for linear operator to vector, which means rearranging entries of the linear operator as a column vector. The solving procedure can be basically shown like this. The first error is using the matrix fact to extract the row in the equation to the right. After this step, the equation becomes an ordinary linear differential equation. We can easily get the solution of it, and thus we know how the density operator changes over time. And then we come to the formal definition of quantum continuous time Markov chain, or QCTMC for short. It consists of an enlarged Hilbert space formed by a finite set of classical states, each of which has a Hilbert space attached to it. And the transition function corresponds to the Lindblad's master equation, which is given by a Hermitian operator and a finite set of linear operators on the enlarged Hilbert space. An explicit example is shown below. There are 4 classical states, S00 to S11. There is a 2-dimensional Hilbert space attached to each state. As we want to look deeper in the interaction between states and the environment, we ignore the internal transition and set H to be 0. We use only one linear operator to describe the interaction, which consists of 6 atoms. Each term corresponds to a transition between the states. For example, when transition takes place from S00 to S10, the outer product operator 0 plus acts on the state at S00, whose resulting state is then transformed to S10. So the system will run in this way over the time, and we are interested in some real-time property of this system. So we introduce signal temporal logic, or STL, which is widely used to express real-time properties. This logic is expressive as its atomic propositions can be interpreted as signals. It's of the polynomial constraint form Px in I, where x is a vector of s variables, and we can determine where the STL formula is true or false in the system at some time stamp. So there are some logic connectives, negation, and conjunction. Also, an until operator is useful to describe real-time property. Here are the semantics of the STL formula interpreted on a QCTMC. For the atomic formula, every axis is a trace of density operator on state X, interpreted as a probability at state S. The negation, the conjunction, and the until formula has the standard semantics. So how can we determine the truth of a given formula? We will firstly solve the basic part, the atomic propositions. The atomic proposition can be transformed into algebraic structure phi, the form of which is shown as an exponential polynomial. The beta parts are polynomials, and alpha 1, alpha 2 to alpha m are distinct algebraic numbers. The atomic formula is true if and only if the phi t is less than 0. So the main point is to isolate the real roots of phi. So the whole isolation procedure is shown as a flow chart. Firstly, after the input of exponential polynomial phi t, and the basis funding part, we construct a q-linear independent basis mu1 to mu k of those exponents alpha1 to alpha m we just mentioned. In the following steps, we use this mu to replace alpha. Then we treat each exponential exp mu t as a variable. Thus, we get a k+1 variate polynomial representation f of phi t. Next, factor the k+1 variate polynomial obtained from the previous step into irreducible factors fi. Then we need to judge whether it has only univariate or multivariate. If an irreducible polynomial is univariate, we resort to classical method. Otherwise, we use algorithm 1, which is exactly designed for real root isolation of the exponential polynomials occurring in this work. Based on Shanel's conjecture of the roots besides 0 from different factors do not coincide. So we can refine the isolation intervals to be parallel disjoint intervals. Next, I will introduce algorithm 1. The main idea with this algorithm is to divide the given interval recursively until it decisively includes only one root or none. Thanks to Shanel's conjecture, all the root is of an irreducible factor are simple roots. Here we set n as 2, so we will divide the interval into two subintervals to search the root. In line 4 and line 5, if the conditions are satisfied, there is no root in the neighbors, so we jump these intervals. And in line 6 and line 9, if the conditions are satisfied, the function will be monotonous in the neighbors. So if the function has different signs at the endpoints of interval, there is exactly one root in the interval. Or if they have the same sign, then there is no root in the neighborhood. Thus we get the intervals. After solving the atomic propositions, we further consider the formula without the negation, conjunction, and until operators. Here, post-monitor period is a useful definition. It means that to determine the truth of formula at time t, one must post-monitor a time period. For example, if we want to find this until formula, it's true or false at time t0. We have to monitor the states rho t from time t0 to t0 plus the supreme of these two until intervals, I1 and I2. We can calculate the post-monitoring period as following. For atomic propositions, the MNT is 0. Negation formula will not change the MNT. And for conjunction of two formulas, MNT will be the maximum of the two periods. For until formula, we need to monitor the whole until formula, besides which the MNT for each subformula should be also considered. And then let's see how to get the solution set of STU formula. We can deal with the formula as a parse tree, so the leaf nodes are atomic propositions and the negation, conjunction, until part become the middle nodes of the tree. We solve it in a bottom-up fashion. After getting the solution set of leaf nodes, if we meet with negation node, the solution will be the complement. And if we meet with conjunction node, the solution will be the intersection of the two child nodes. And the solution set of until node how to satisfy that switch point t prime in interval I, and the time between current time and switch time is the subset of J1, and the switch point is in the J2. Thus, the main method of this work are all above. Then I'd like to apply our method in an interesting example. Here, open system quantum walk is a quantum analog of random walk. Imagine a particle walks along the 2D hypercube shown in the figure I have mentioned a few slides ago. It starts from the position x0 and where x1, which is an absorbing boundary. S01 and S10 can be seen as transient positions. There are two directions it can choose, F and S, in where F means the particle takes a transition along the first coordinate, for instance, walking along S0 to S10, while S means the particle takes the transition along the second coordinate, like S00 to S01. At every moment, the particle has to choose a direction by quantum coin tossing. The probability of both directions are the same. The coin tossing is implemented by Hadamard operator, and the transition function of the whole process is as follows. As the particle comes and goes, it's natural to ask how fast the particle would reach the exit, which can be named as convergence performance. This convergence performance can be described explicitly as follows. At each moment, in the first 5 units of time, whenever the probability of staying at those transient positions, S01 and S10, is greater than 1/5, the probability of exiting would exceed that of transient positions within the coming 1 unit of time. It can be formally specified by STL formulas as follows. A little bit notation here, as X01 stands for the probability of staying in position S01, and so is X10 and X11. And we only consider the transformation of the system from 0 to 6 units of time. So still we solve the atomic propositions. First of all, we get the exponential polynomials of both phi1 and phi2. After invoking algorithm 1, we can get the isolation intervals. For phi1, there are these 2 isolation intervals. And for phi2, there are a single root, a 0, and n interval. Note that 0 cannot be dealt with, but we can just check it by substituting 0 to the exponential polynomial. So get the solution set for these atomic propositions, of which phi1 is lambda1 to lambda2, and phi2 is 0 union lambda3 to 6. And we can depict the STL formula as a parse tree. In the previous step, we have already get the answer for leaf nodes and also the monitor period, which is pointed out behind the comma. According to the method we had just mentioned, we can further get until node here and compute its complement to get negation node here, and use the intersection of these 2 nodes to get solution of the conjunction node, and still the until node. Finally, we can get the solution set. As phi1 is about the property of the system at time 0, and 0 is obviously not in the solution set. So we can decide the STL formula to be false on this model. To sum up, our contributions are threefold. Firstly, we initialize the model checking STL on quantum CTMC. Secondly, in the solving part, we develop a state-of-the-art real-root isolation algorithm for a rich class of real-valued functions. Thirdly, we study open quantum walk equipped with an absorbing boundary as a running example. Thanks for your attention.
Thank you, May. Again, is there a question?
Hi, Yusuf.
Is there a question from the attendance? No hands raised, no question asked. Okay, so I have maybe a naive question. So you introduced the model checking against STL formulas.
Yes.
But one can wonder whether one can only be interested in, let's say, LTL formulas on this kind of quantum systems. That, for example, maybe the system designer is not very much interested in the time passing or the quantitative nature of the formula. And for example, for your quantum random walk, you can ask only if I can reach the exit state, not within a specified timestamp or signals. And this problem was, I was wondering if this problem was considered before or not.
Oh, thanks
or
for
maybe
your.
It cannot be initialized.
Oh, we haven't thought about this question before. And you mean time maybe not
instead of
important
considering
in
STL, yeah,
not important in the quantum model?
in the formula.
Okay. The formula describes the signal changes over time, and also in quantum model, we can focus on the speed of the model changes over time, and some real-time property. So
Okay.
I don't really.
Okay, so maybe another quick question. Does it make sense to ask about the complexity of your root isolation algorithm, or?
Oh, okay.
Or is it too high?
The algorithm one, the real root isolation algorithm, it is still an open problem for the complexity of this algorithm. But the query because the while loop in this algorithm is we can know the recursive depth of the while loop, but we can sim this while loop as a oracle, which is commonly used in quantum computation, and we can call it as a query, and the query is linear to the input, the size of the input formula. And we believe this algorithm is a polynomial for most cases, and we can run it in our case.
Okay, thank you. A quick check
thank you.
On questions. So I can't see any questions, so maybe we can stop this session here and thank all the speakers and the audience, and we can already start enjoying our break. So